In the last video, we talked about Eulerian circuits. In this video, we're going to talk about Hamiltonian circuits. And both of these are named after the mathematician who first discussed them, proved things about them, showed that they were important. So Hamiltonian circuits are a bit newer than the Eulerian circuits we talked about in the last video. In fact, Sir William Hamilton, first brought them up about 100 years later in 1859. And the idea is very similar to an Eulerian circuit, except now we don't care about hitting every edge, but we care about hitting every vertex exactly one time. So a Hamiltonian circuit is a simple circuit, and that's important. That includes every vertex of G. Okay, so that simple circuit is important. It means we're not repeating any vertices, we're not repeating any edges. All right. And then if that's the case and we cover every single vertex in the graph, then we've found a Hamiltonian circuit. So here's one for this graph. Okay, we can come over here, hit that one, here. And we come around. There we go. And notice how we've covered every vertex, but we've never duplicated the vertex except for the start/end point right there. And we've duplicated no edges. So it is a simple circuit and a Hamiltonian circuit because we've covered every vertex in the graph. Unfortunately, unlike an Euler circuit, there's no easy way of determining if a graph has a Hamiltonian circuit. Okay, so we can't determine, there's no formula, there's no way of easily doing that. We do know ways of ruling out graphs to say that they don't have Hamiltonian circuits. And to do that, we can say that if a graph has one, then G has a subgraph H with the following properties. H contains every vertex in G. H is connected. The number of edges and the number of vertices are the same. So I'm going to do the size of the edge set of H is going to equal the size of the vertex set of H. And finally, every vertex in H has degree 2. All right, so we can enter a vertex and then leave. And since we're never going to come back and touch that vertex again, that's all we need. We need exactly 2. Okay, so we want to look at these graphs and say which of the following have a Hamiltonian circuit. Well, this first one, my intuition is that it doesn't, because we get to B, but in order to get back over here, I've got to go through B again, and that's not allowed. So you can try it a couple of different ways. We can say, okay, what if I start at B? Nope, I've still got to go back to B. If I start over here, right? it's going to turn out that there is not a Hamiltonian graph here, and we're going to get to why. But the intuition is that it's because we're going to have to visit that vertex twice. Intuitively, but that's not a formal proof, and that's not using the definition and the rules of a Hamiltonian circuit that we need to. So that's the next slide, but for now let's look at this other one over here, and let's see if we can make this Hamiltonian circuit. Yay, we found one. And just because I know the answer ahead of time so I can find it easily, but sometimes these can be very difficult to find. And that's part of the problem with Hamiltonian circuits. But this one does have one, so we're good. So as promised, we're going to come back to this graph and we're going to prove that there's no Hamiltonian circuit. So does it have a Hamiltonian circuit? No. And once again, we're going to do a proof by contradiction. It's a very common proof type. For graph theory. A common one that we haven't really seen yet is also proofs by induction. Proof by induction is very commonly if we're trying to create a graph that has some property and we can demonstrate that a subgraph has that property. You can use a proof by induction to do a lot of this as well. But here we're just using a proof by contradiction. So the first thing I want to do is I want to suppose the opposite. So suppose there is a Hamiltonian circuit. Well, what does that mean? Well, that means by our rules of what makes up a Hamiltonian circuit right here that we talked about earlier, that means that we're going to have a subgraph. Then is this a subgraph? H, such that every vertex in H has degree 2. In H. Now there are other rules, but this is where we're going to find our contradiction. Okay, so since every vertex in H has degree 2, we're going to have to lose 2 edges. Because otherwise this B vertex, it has degree 4. So in H, it's going to only have 2 edges. Okay, so we're going to lose some edges. Maybe let's cut out that edge and that edge. The problem now becomes if this top edge is crossed out, then A only has a degree of 1, right? And so would D. And in fact, whichever edges were cut out, the associated vertex on the other side of that edge would go down to degree 1. So there's A, C, D, and E. And these would have to lose an edge, dropping to degree 1. But we said they all have degree 2. And there's our contradiction. There we go. So that is our Hamiltonian circuit. In the next video, we're going to go over a problem that uses Hamiltonian circuits, and it's a very relevant, important topic in computer science.